So let's start. We defined what it means for a function to be injective, surjective, and bijective last time. Today we're going to talk more about functions. We're going to prove some basic facts about functions, and then using the notion of a function, we're going to define generalized Cartesian products, generalized products. Okay, but let's first prove some basic things about functions. So we defined what it means for a function to be injective. That notion can be generalized to relations. Okay, the notion of injectivity can be generalized to relations. Okay, so how do we do that? A relation R is said to be injective if the following happens. When R relates two guys to the same object, those guys are the same. Okay? So this is just like the definition of injective function, except you just put an arbitrary relation. Now let's make an observation, which is the following. Let's take a relation. This relation is an injective function if and only if its inverse relation is an injective function. Okay? Not that this lemma on its own matters too much, but we're basically like practicing. We're trying to internalize these notions. So let's prove the left to right direction. Assume that R is an injective function. Then, now, what does it mean for a relation to be a function? R is a function if the following happens. Okay? When x is related to two guys, those guys are the same. Yes. Sure, but you weren't here last time, right? Our definition of function differs from, okay, we defined a function to be a simply set of ordered pairs which satisfy this property. So when I talk about a function from some set to some set, you say that there should be no element not defined in the domain. But when I simply talk about a function, when I don't specify a domain, it simply means that it's a set of ordered pairs satisfying this property. That's it. So a relation satisfying this property is a function. The domain of function is blah blah, the set of all sets such that something happens. We defined those last time. Okay? So go back to the notes and read the definition. You'll see that for us, a function, if I don't specify in domain, is simply a relation satisfying this property. Okay? Now, if you remember the definition of the inverse relation, X and Y are related if and only if when X are related by the inverse relation. So this claim can easily be converted to this claim. But what does this mean? This simply means that our inverse is injective as a relation. Okay? So maybe I should add this. Since R is a function, we have this claim, and this implies that our inverse is injective. Now, I just proved that this is an injective relation. I don't know that it's a function. Now, let's use the fact that R is injective. Since R is injective, we have the following claim. For all x, for all y, for all z, x related to y and x related to z implies that y equals z. And so I'm going to do the exact same thing. I'm just going to use the definition of the inverse relation. Now, if you read this, this is exactly what it means for R inverse to be a function. R inverse is a relation. It's a well-defined relation. This is the property of being well-defined. Where is y is mapped to x? Sorry. No. I wrote it this seems wrong. ZX. Sure, you're not stopping me. Yes, okay. No, something is off here. What is off? You're not stopping me here. Injectivity doesn't mean this. It means the following. X is mapped to Z, Y is mapped to Z, then X is Y. Obviously. We use the other thing over there. Injectivity means this. X is mapped to Z, Y is mapped to Z, then X and Y should be the same. Now, if you use the definition, you'll get this. And this is what it means for R inverse to be Zx, Zy, and Xy. Exactly. Now, this is what it means for R inverse to be a well-defined relation. In a well-defined relation, an object is related to only a single object. So Z is mapped to X, Z is mapped to Y, and in this case, X and Y should be the same. So this is the same as saying that this is well-defined. So we just showed that if R is an injective function, well, and tense is a function. Tense is a function. We just showed that if R is an injective function, then so is R inverse. Now do the symmetrical argument. By a symmetrical argument, which I'm not going to do, obviously, we also have that if R inverse is an injective function, then so is R injective function. Okay? So what's the point of me doing all this? This is just to make sure that you internalize the fact that injectivity and well-definedness are somehow related. A relation is well-defined if and only if its inverse relation is injective. Okay? That's simply by definition, actually.
So we can use them interchangeably, right?
No.
No. Like if it's an if and only relation.
You can use this. Well, if you have an injective function, its inverse is an injective function. Its inverse relation is an injective function.
I mean about well-defined, but if function is injective, then it's well-defined?
No.
If it's well-defined, it's injective.
No. If a function is well-defined, its inverse is injective. If a function, if a relation is well-defined, then its inverse is injective. If a relation is injective, its inverse is well-defined. So they're not the same. Okay.
Inverse relation is similar.
What?
Like inverse. Injective implies inverse is well defined.
Yes, yes. And the other way around as well. Anyway, now let's introduce some more terminology. Now, you can easily check that. What's a function? A function is a relation which is well defined. The property of being well defined, namely this property, you see it passes to subsets. What do I mean by that? If a relation satisfies this property, then so do all of its subsets. So if a relation is a function, then any subset is a function. Okay? Now we're going to name to those subsets. Given a function f and a set A, which is a subset of the domain, we define the restriction of f to A to be the following function. It's denoted like this, f restricted to A. This is the set of all ordered pairs such that x is mapped to y, we have this function, and x comes from A, okay? This is the usual notion of restriction that you knew. Well, I told you last time I'm going to stop using this notation and I'm going to simply write f of x equals y, okay? Because that's the proper way of writing things. Like when I say proper, I mean it's what we do when we actually talk about functions in practice. So that's the restriction of a function. What else do I want to talk about before starting products? Okay, let's talk about compatible functions and unions of functions. Definition. Two functions f and g are said to be, bless you, compatible if for all sets which is in the intersection of the domains of these functions, we have that these functions agree on the values, okay? So pictorially, you have a function f, you have a function g, and if there's an intersection of the domains of these guys, on the intersection, these functions should behave the same, okay? Okay, I'm not going to try to finish the picture. Now, any lemma if you have two compatible functions, then their union is a function. Let's prove this. So how do I prove this? What's a function? Again, these are all just to internalize these concepts. So what's a function? It's a relation satisfying a certain property. So, first of all, is this a relation? Well, this is a set of ordered pairs. This is a set of ordered pairs. The elements of the union are coming from these two guys. Therefore, that's the set of ordered pairs. So that's a relation. Now, I have to check that this relation is well defined. Okay? We need to check that this union is a well-defined relation. So let's check that. Let x, y, z be sets such that, okay, maybe I don't use the function notation at the moment. I use the old notation. Pick three sets such that x, y belongs to this union and x, z belongs to this union. I want to prove that this union is well defined. It's a well defined relation. So I need to prove that when x is related to y under this relation and when x is related to z under this relation, z actually equals y. We wish to show y equals z. Now, there are 4 cases that can happen. The first case is xy belongs to f and xz belongs to f. You see, you were supposed to prove as an exercise that whenever a set belongs to a union, whenever a set belongs to the union of two sets, then that set belongs to either the first one or the second one. So the first case is that this happens. Maybe I should call this case 1. In this case, since f is a function, y equals z, because I just used the fact that f is well defined, okay? Case 2, or do I want to split into more cases than this? No, I don't need that. The second case is both of them could come from G. In this case, the same thing happens. I use the fact that G is well defined. Okay, this is a well defined relation, so x is mapped to y, x is mapped to z, y equals z. Case 3, the first one comes from f, the second one comes from g. In this case, we use the compatibility assumption. Now, x belongs to the domain of f, by definition of the domain of a function. X belongs to the domain of G. By compatibility, for all values, for all sets in the intersection of the domains, these functions take the same value. So y should be z. Since these functions are compatible, we have y equals z. And in the fourth case, the same thing happens. Okay? The fourth case is the first one comes from G, and the second comes from F. We have the exact same thing happening.
Okay.
Yes?
As I understood, elements of functions are couples, right?
Yes.
How, like, is it possible? The element of domain, like, function takes 2 values.
No?
No?
Were you here last time?
Yes.
Okay. What's a relation? What's a function?
Takes into
No, that's not the definition of a function. How did we define the function?
equation.
Exactly. So before we start the class, maybe I didn't say this. Everything you learned about set theory and functions and relations, simply forget them. They're wrong. Either incomplete, wrong, or misleading. Forget the definition of the function you know. Tell me the definition of the function that you learned last time. What's the function?
It's type of relation.
It's a relation which satisfies a certain property. What's the relation?
It brings two elements from two sets together, right?
It's a set of ordered pairs. No, forget about rules. What's the definition of a relation? A relation is a set consisting of pairs, ordered pairs. A function is a special type of a relation. So what's a function? It's a set of ordered pairs. No, there are no rules satisfying some property. Forget the rule part. So a function is a set of ordered pairs satisfying a property, namely the property of being well defined. Okay? So this is a set of ordered pairs. So its elements are ordered pairs. We interpret this ordered pair belonging to F as F sending the element X to Y. So it's not the case that it takes two inputs. This notation simply means, in the usual sense, X is mapped to Y under F. Okay? Okay. So compatibility simply means that for all X in the intersection of the domains, I have this. So this means that this is true. Well, by compatibility, Y should be Z. Now, again, I repeat this because it's going to create a problem. A function, all the stuff you learned in high school are simply wrong. That's the fault of the Turkish education system, okay? Forget about all those definitions. Like a function is a rule which takes an input, blah, blah. That's how we think of functions in practice. When you formalize functions in set theory, functions are relations satisfying the property of being well defined, okay? So a function is a relation which satisfies that sentence which was over here, okay? Like 5 minutes ago. Questions? No. Now, I'll assign you an exercise now that I did this. Let me assign it over here. Let S be a set consisting of functions which are pairwise compatible. Pairwise compatible means that any two of them are compatible. Any two are compatible. Show that, prove that. Now this is a good exercise. If you want to understand how we treat functions in ZFC, show this. Show that the union of S is a function. Everyone remembers the definition of this. Union of a single set. Union of a set is the set of elements of S. Meaning that you take the elements of S and take their union. So if you have a set of functions, then this guy, the union of S, is simply the union of all these functions. What I claim is, if all these functions are compatible, then the union is a function. The point is, I can do this with arbitrarily many functions. I don't really need two functions here. I can have infinitely many functions if you want. If all those are compatible, when you take the union, it's going to stay it's going to be a function, okay? So prove that. You're going to prove that this is first a relation which is obvious. You can skip that step. The point is proving that this is well defined, okay? And let me write this. A relation is well defined if and only if the following happens. And again, just to emphasize this, R is a function if R is a well-defined relation. That's it. Okay?
While proving this exercise, do we have to use axioms, or can we assume that axioms are true?
I don't expect you to actually go to the level of the axioms. You don't have to explain like I use this axiom to justify this. You can use all the axioms I introduced so far, but not the ones I haven't introduced yet. Okay? Now, oh, and also prove that, let's make an addition to this. Prove that the domain of this function is the union of the domains. Okay? Now, when we proceed, we're going to go back to, okay, I was a bit harsh when I said forget everything. You really shouldn't forget everything, otherwise we won't be able to communicate. But the point is, in practice, we treat functions as rules that takes one input, produces one output, blah, 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 blah. And in future, we're going to keep doing that. But you should never forget that for us, in set theory, a function is simply a well-defined relation. It has members. Its members are ordered pairs. So a function, it's just a set. What are its elements? Its elements are ordered pairs. What does it satisfy? It satisfies this property, okay? This is the definition of being well-defined. So it just satisfies this property. Okay? Intuitively speaking, yes, it's a rule that does blah, 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 blah. But that's intuitively speaking. When you need to prove things like this, you need to treat functions as they are. Now, let me show one more thing. Again, this is just to make sure that you internalize these concepts. Lemma. If you have two functions, then the composition is a function. Now, you'll probably say, of course, this is a function because, like, when you learned composition for the first time, you learned the composition of functions. But I gave you a more general definition, right? There's the notion of composition of relations. These are relations. This is the composition. Let's prove that this is also well-defined whenever f and g are well-defined, okay? If you have two relations, their composition relation is obviously a relation, just by definition. We just want to prove that whenever these relations are well-defined, then so is their composition. Okay, so by definition, this is a relation. Why? How did we define the composition of two relations? This is the set of all ordered pairs, such that there exists some guy satisfying the following property. X is mapped to this guy under the first function, and this guy is mapped to the second guy under this function. Okay? Now, again, yes, as you said, a relation is a rule that relates something, blah, blah. A relation is a set of ordered pairs. Is this a set of ordered pairs? Yes, so this is a relation. Now I need to check that this relation is well defined. We wish to show that this is well defined. So I need to assume that f and g are functions, obviously, otherwise it's not going to be true. How do I show that a relation is well defined? I just check that property. Let x, y, z be sets such that x, y belongs to the composition and x, z belongs to the composition. I want to prove that y actually equals z. So how am I going to do that? The only thing I know is the definition of this composition. So let's use that. By definition, there exists u and v such that xu belongs to g and uy belongs to f, and xv belongs to g and vz belongs to f. Okay? I just opened up the definition of this. When is an ordered pair an element of this composition? If there exists some set, which I called U, satisfying this. XU belongs to this guy, UY belongs to the second guy. And similarly, there exists some other set V such that XV belongs to this guy, VZ belongs to the second guy. Now I'm going to use the fact that f and g are functions. Let's first use the fact that g is a function. What's the function? A well-defined relation. Because g is well-defined, xu in g and xv in g implies that u equals v. Now I'm going to use the fact that f is a function. You see, I knew that uy belongs to f and vz belongs to f. I just proved over there that u equals v, so these two guys are the same. Because f is well defined, their second components are the same. So y turned out to be z. So this composition is well defined. When x is mapped to two different guys, they're not really different, they turn out to be the same. So composition of two functions is a function. Now an exercise. This is about the domain stuff you were talking about. We defined what it means for a function to be a function from something to something, but a function by itself is simply a well-defined relation. And its domain is the set of all guys you see as the first components, and the range is the set of all guys which you see as the second components. Okay? So let f and g be functions. Show that the composition is a domain. The composition is a function, right? So to show that the domain of G composition F is the following set. Domain of F intersection the inverse image of the set domain of G. and that on this set for all x in this set this holds. Okay? And we probably learned this as a definition before. Like, how did you define compositions, like in calculus or in some other courses? You learned this as a definition. Well, I just defined this in a different way, but it turns out to be equivalent to that definition you learned before. Anyway, so these are just, think of these as warm-up exercises, okay? Before warming up your muscles, if you try to backflip, you're gonna hurt your spine or something. You're gonna die, okay? Think of this course like this. If you don't warm up, the things that are about to come in 2 or 3 weeks will start to hurt. So make sure that you solve these and like you have enough skills to basically follow all the proofs quickly. Now, I have 10 minutes in the first lecture. Let me define the following set. This is actually important. We're going to use this notation a lot, the notation I'm about to introduce. Now, given two sets, x and y, it follows from the axioms we've introduced so far that the collection, now let's stop over here. So I want to collect all functions together, satisfying the following properties. This is, okay, I'm collecting all sets. First of all, this set should be a member of X Cartesian Y, meaning that F is a relation from X to Y. It's a subset of, F is a subset of X cross Y, so it's a relation. I want F to be well defined. Now it became a function. So why is this a set? We just use the axiom of separation. Given and axiom of power set and so on actually. We use a lot more. Given two sets, we constructed the Cartesian product last time, right? Say yes? Yes, we did. Everybody remembers. So we constructed this. This is a set, the set of all ordered pairs where the first component comes from X, the second component comes from Y. By power set axiom, this is a set. By the axiom of separation, when you have a set, the set of elements of this first set satisfying a certain property is a set. So this is a set. And this is the set of all functions from X to Y. And this is denoted by the following notation. Or sometimes people use y to the power x, okay? So this is important because we're going to define, for example, cardinal exponentiation using this concept, okay? Whenever, for those who are already familiar with this kind of stuff, given two cardinal numbers, a and b, the cardinal number a to the power b is the cardinality of the set of functions from B to A, okay? So we're going to use this set a lot. This is the set of all functions from X to Y. Now, yes?
This part, this Pxy is like
the power set.
Power set of this cross product of X and Y, right?
Yes, the Cartesian product, yes. So this is basically all subsets of X cross Y, okay? In other words, this is the set of all relations from X to Y. That's another way of stating that. Now, we have this notation, and, well, not just the notation, this concept is important, the set of all functions from something to something, okay? Now we can start defining the product of a collection of sets, an arbitrary product. Okay, so products and sequences. Where's all my white chalk? It's gone. I can't use. I'll use this one. It's visible. Can you turn on the lights? Thank you. So, we defined the Cartesian product of two sets. I want to generalize this. Okay, here's one generalization, which is going to sound stupid. I can define the Cartesian product of three sets, obviously. Just first take the Cartesian product of these two, then do this. I can keep doing that. Okay, what if at this moment we don't know what a natural number is, what's the set of natural numbers, but pretend that we do. What if I have a set, A, B, C, D, E, dot, dot, dot. I have a set for each natural number, and I want to multiply them together. I want to, when I say multiply, I want to take their Cartesian product. So I want to generalize the notion of Cartesian product. Yes, I can do this like threefold Cartesian product, fourfold Cartesian product. What if I want to take the Cartesian product of infinitely many sets at the same time? How am I going to define that? Any ideas? First of all, let's make some observations that's going to motivate the definitions that I will write. Let's get rid of these guys. A cross B. This is a set of all ordered pairs where the first component comes from A, second component comes from B. Now this is a very similar object, except they are not the same set, right? Over here, the first components come from B, the second components come from A. There's a bijection between them, but they're not really the same object. In the set theoretic universe, they're different objects. What that tells you is that if you want to take Cartesian product, you need to have an ordering. Like, obviously there's a bijection between them, but as objects, they're different. So how I order these sets when I take the Cartesian product actually matters, okay? So pretend that I want to define this, whatever this dot 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 means. This basic argument shows that I have to give some ordering. I have to somehow be able to order my sets. But we don't know what an order is. And I don't really need to order them. Like, maybe you have so many sets that you can't order. This is actually false, but pretend that it's true. I don't really need an ordering. What I need is a labeling. Let's get rid of these. Over here, this is my first set. This is my second set. And this is my third set. And when I multiply it like this, I have a label for each set. So these labels I need those labels, okay? I need to talk, because like that basically tells me how am I going to take the Cartesian product. Now there's an ordering on these labels, like 1 is less than 2, 2 is less than 3, and so on. But maybe I do something like this. There is still an ordering. For each real number, again, we don't know what a real number is, said theoretically, but you have an intuitive understanding, so let's stick to that. Don't forget about real numbers. You can forget about the rest, but remember things about those. Pretend that for each real number, I have a set. For each real number, I want to take the Cartesian product of all these guys. There are uncountably many sets here. You know what uncountable is from first year. There are uncountably many sets. I want to take their Cartesian product. What am I going to do? First of all, why do we need this? Because we actually use this notion in practice a lot. Okay? So we need this notion of an arbitrary product. You want to be able to generalize the notion of Cartesian product to arbitrarily many sets. So that's our aim. How are we going to define this? Let's write down some basic observations that we did after a 10-minute break. Okay, be back here at 12:40.